Okay, so we are on section 2.3 and it covers linear independence, span of basis dimension. So we have covered a lot, discussed clearly a lot in linear uh, independence dependence. Right? So we should now have like at least very basic understanding of when vectors are independent or dependent graphically as well as algebraically. Correct? And last time we talked about the span. What do we mean by span of vectors is essentially what we were saying earlier as the space generated by certain given collection of vectors. Right? Hopefully we'll cover what is mean by basis of vector space and the number of vectors in the basis we'll call dimension. So we'll formally define everything. Alright. So since last time most of you already focused towards the exam, let's quickly uh, cover back what do we mean by spanning a subspace and what is vector space spanned by collection of vectors. Okay, so before starting the formal definition of uh, space spanned by a collection of vectors, let's see geometrically what does that mean. So the question is, what is the subspace spanned by V is the collection vector V is equal to 1, 1. So earlier we were saying space is generated by 1, 1. So what is the space generated by 1, 1? R2? Yeah. Y is equal to xi, and that graphically simply means that the line passing through this vector is 1. Right? So bring in the scale. Right, so let's say V is your somewhere around here. So V is equal to 1, 1. Right? Then space generated by V means what? That if you scale the given V, then to what point you can get. Right? So that this V is pointing that way. Now if I scale V two times, then I'll reach here. 3 times I'll reach here. Minus 2 times, if I do the minus 2 reach, I'll reach somewhere around here. Right? So that means how much, if I scale V, how much to what point I can get, and that's exactly what we say the space is generated by V, and that's exactly what we mean by space spanned by V. Okay? So the space spanned by V will be, bring in some other color, there's nothing but will be nothing but the space this one. Alright, let's try to assume it's passing through origin. Okay? So the line, so the space is this space nothing but line passing through V and origin. We have to specify each one, because otherwise there are millions of lines passing through V. And algebraic definition of the space spanned by V is nothing but you just write this in a set form, right? So this is equal to all the vectors to which I can reach to by scaling V. So they're basically the space spanned by V is collection of all the vectors alpha V. That is nothing but all given for different value of alpha. You have different alpha V. Alpha belongs to the set of V. Similarly, what can we say about the space spanned by the set of vectors S equal to this is by definition it's nothing but so that's nothing but in algebraic definition it is nothing but all the vectors I can reach to by taking scalar combination of individual vectors and adding them together. Right? So it's nothing but alpha 1 1 plus beta 1 0 such that alpha and beta belong to alpha. Right? And geometrically, what do we know about that's nothing but so there's 1 1. V is equal to 1 1 is placed somewhere around here. That's V, and the other that's first vector, and the second vector is around somewhere around here. Okay. That's V1 and that's V2. So what does this expression mean? So this alpha V1 means any vector on this line. L beta V2 means any vector on the x. So together, if I want to reach somewhere around here, then I can scale this thing around somewhere around there, scale V2 around somewhere around here, and basically you can add these two vectors to get this. Okay. So essentially, by scaling and adding these two vectors, I can reach the whole of the structure. Then this collection, as I mentioned, saying that this set is nothing but order. That's order. But that keep in mind that this is just the geometric interpretation of this. As far as the definition of linear span goes, you are just restricted to this. The linear span of collection of vectors is nothing but a collection of linear combinations of vectors. Right? Okay, so we can add some more vector in it. So the first subspace spanned by this set of more vectors. Again, given any collection of vectors, linear span of the vectors is nothing but the collection of linear combination of them. So that should again nothing but alpha 1 1 plus beta 1 0 plus gamma 0 minus 1 such that alpha beta gamma are 0. Right? So the again space spanned by these three vectors is just that. After that, whatever you're doing, you're just being a good mathematician and saying, okay, what exactly is this dimension? And again, we already know that the space spanned by 1 1 1 0 is R2. Whatever another vector you can add to it, this again this vector in R2, so you can add two vectors on real line, you are still going to be in R2. Right? So that's again R2. So again, once I have to emphasize once again that if the question is what is the linear span, you do not jump and go ahead and say answer is R2. Okay? That's not the right answer. Linear span is that. Right? It's possible that you have 1 1, you have 2 2, you have 3 3, and the linear span of them will be alpha 1 1, beta 2 2, gamma 3 3, and they all just add up on the same line. So in that case, answer will not be R2, answer will be just a line passing through 1 1 or 2 2 or 3. Okay? Questions? Any confusion? So formal definition of space spanned by collection of vectors is again what I was saying, that if S is a collection of m vectors, V1 to Vm set of vectors, then the linear span of the space it's R2 actually. No, so what will happen in that case? If this is 1 1, that is 2 2, they're on the same line, right? Right? You can scale 1 1 any way you like, they will be on the same line. Okay. what I'm saying. So if we have that kind of vector, then we have still the definition of the linear span will be alpha 1 1, beta 2 2. But eventually, geometrically, what does that set look like? That's nothing but the line passing through it, not the whole apartment. Okay, so we were on the formal definition of space span by. So that's nothing but if you have collection of vectors v1 to vm, then the space generated or the space span by S is nothing but another collection of vectors where each of the vector is formed by linear combination of the given vector. Okay. Any questions? Alright, so till now we took a collection of vectors and we defined what do we mean by the linear span of those vectors. Right? So if you have noted that we were all the time saying that the collection of vectors or subspace generated by collection of vectors or the subspace spanned by collection of vectors. But we have to be careful when we use terms something like subspace. Right? So we are saying that it's a subspace, but we never actually proved that the collection of vectors spanned by given set of vectors is actually a subspace. Right? So let's do that very quickly. Right? So what we are saying that if S for any collection of vector S from V1 to Vm, any collection, actually this is something different. I'll come to that. So the theorem is for S is any collection of vectors in Rn. Okay, make sense? So this S subset of Rn means Rn is basically collection of vectors. So we take a fixed collection of vectors in Rn, and we are saying that Ls, our standard notation, will be our standard notation for the linear span of it. We will say that this is always a subspace of Rn. Okay. Who can tell me what's a subspace? Yeah.
Belonging to the subset x plus y belongs to the subset of V where x and y also belong to the subset, and the linear combination also is subset of
Linear scaling. Scaling, right? Alpha. So geometrically, what does that mean? A subspace of Y is a vector space among itself. Okay. What to remember when you remember a vector space? Vector space has two things. So if we add two things in the collection, the sum will stay in the collection. Alright? And there's alpha scaling and some scaling of that will again stay in the collection. Right? That's why we have a line passing through origin is again a subspace in R3. Okay? Because it preserves all that order, and if you add the two vectors in the line, you get a vector in the line. If you scale a vector in the line, you say that you get a vector in the line. Similarly, a plane inside R3 passing its origin is a vector space in itself. Because if you add two vectors in the plane, you get a vector in the plane. If you scale a vector in the plane, you again get a vector in the plane. Alright? So essentially what we have to show that linear span of is again a vector space in itself. Now vector space has